Hi, in this video we are going to see an important application of the convolution property of the Fourier transform. But first let us remember what we mean by the convolution property and how we apply it in the input-output relationship, input-output signal relationship in LTI systems. So let us consider a linear time invariant system. And the input is x of t, the output is y of t, and the impulse response is h of t. It is the output of the system corresponding to a unit impulse at the input. We know that y of t is the convolution of h of t and x of t. Now this is a general result valid for a linear time invariant system. It can be stable or it may not be stable, but still this relationship holds. If in addition, if the LTI system is stable, this means that h of t is absolutely integrable. Meaning that from minus infinity to plus infinity, the integral of the magnitude of h of t is finite. It's a convergent integral. Now, in this case, we know that if a signal or function is absolutely integrable, its Fourier transform exists. So, Fourier transform of h of t, known as h of omega, exists, and we have a special name given to h of omega. It is called the frequency response of the LTI system. Okay, so h of omega is the frequency response of the stable, now this is the important concept in this case, stable LTI system. So the frequency response exists only for stable LTI systems. If the system is not stable, then the frequency response does not exist. Now, in this video, we are going to study the so-called ideal filters. Ideal filters are specific LTI systems which pass certain frequency components and reject the others. And this is called the filtering action. Okay. So we start with the first ideal filter and the most well-known among these ideal filter types, the ideal low-pass filter. Okay. Now we are going to specify the frequency response as follows. H of omega, the frequency response of the ideal low-pass filter will be equal to 1 for magnitude omega less than omega c and 0 otherwise. Now, if we plot this frequency response as a function of omega, h of omega is equal to 1 for omega between minus omega c and omega c. Okay. Now, the inequality magnitude omega less than omega c implies that omega is between minus omega c and plus omega c. Why? Because if omega is positive, magnitude or absolute value in this case, because omega is real valued, absolute value of omega when omega is positive is equal to omega. So we have omega less than omega c for positive values of omega. When omega is negative, absolute value of omega is minus omega. So minus omega less than omega c means omega greater than minus omega c. Okay? So, as the name implies, the ideal low-pass filter passes low-frequency components and rejects the frequency components with frequencies greater than omega c or less than minus omega c. Okay, so we have the ideal low-pass filter. So maybe I can write the abbreviation here, LPF. The input is x of t, the output is y of t, and of course in frequency domain, y of omega is equal to h of omega, x of omega. Now x of omega is the Fourier transform of x of t, therefore it gives us an idea about the frequency content of x of t, the frequency components. So all those frequency components with frequencies in the interval from minus omega c to omega c will be passed through the system, and the other frequency components outside that interval will be rejected. Now, as an example, we can consider the well-known impulse train signal, m from minus infinity to plus infinity, delta of t minus m t0. So we have the impulse train, we have the graphical form. We have an impulse at t equal to 0. At t equal to t0, we have again the periodic repetition of the impulse, and at minus t0 we have the impulse. So we have the periodic impulse train. All the impulses have unit weights, and we know that x of t has the Fourier series representation given by from minus infinity to plus infinity. The Fourier coefficient is simply 1 over t0, and we have e to j k omega 0 t. Here, of course, omega 0 is 2 pi over T0. Okay. Now, let us assume that x of t is the input of an ideal low-pass filter with omega c. Omega c is called the cutoff frequency. So, well, this name is in fact clear, cutoff frequency, because all those frequency components with frequencies greater than omega c or less than minus omega c will be rejected. Cutoff frequency of the filter. So let x of t be the input of an ideal low-pass filter with cutoff frequency omega c satisfying the following inequality. Omega c is between, okay, omega c is greater than n omega 0 and less than n plus 1 omega 0. So this means that x of t with this Fourier series representation will pass through the system, and we are going to again obtain a periodic signal y of t which will be equal to k from minus infinity to plus infinity. Okay, not from minus infinity to plus infinity, sorry, from minus n to plus n. Why? Because all those frequency components with frequencies greater than n omega 0 will be rejected. Okay? 1 over t0 e to j k omega 0 t. Okay? So we recognize y of t as the Dirichlet kernel, in fact. Dirichlet kernel dn of t. So high frequency components in x of t will be rejected. By high frequency we mean those frequencies determined by the cutoff frequency, all those frequency components with frequencies outside the range from minus omega c to omega c will be rejected. And if we plot y of t, okay, the plot will okay, be not very easy to show graphically, because we have the at 0 t0 and, for example, let us plot what happens at minus t0. The Dirichlet kernel, remember, is has a special form, a graphical form, with a main lobe and with the side lobes. So if n is chosen sufficiently large, the main lobe will be quite narrow. So the main lobe will be something like this, and we will have the side lobes. And similarly at t0 we will have the main lobe and the side lobes, and at minus t0 we will have similarly a narrow main lobe and side lobes. Okay, so the singular behavior is now replaced by a smooth behavior, rather smooth behavior, because we have continuous y of t turns out to be a continuous function of t, but as we choose the cutoff frequency having larger and larger values, of course the main lobe will become very short duration, and it will increase in magnitude, and it will tend to an impulse eventually. So the action of the low pass filter in this case is to pass only those frequency components with frequencies in the range from minus omega c to omega c, and the other frequency components, the high frequency components, are rejected. Okay, now next we are going to see the ideal high pass filter. So as the name implies, we are going to see that high frequency components will be passed and low frequency components will be rejected. So let us look at that case next. Okay, now next we look at the ideal high pass filter. So we abbreviate this as HPF. Okay, the frequency response of the ideal high pass filter will be just the following: 1 for absolute value omega greater than omega c, and 0 otherwise. So if we plot the frequency response as a function of omega, h of omega is, okay, we choose omega c, which is again called the cutoff frequency. So when omega is greater than omega c, or when omega is less than minus omega c, the value of h of omega is equal to 1. Again, if you look at the inequality, magnitude omega greater than omega c means if omega is positive, magnitude omega is equal to omega greater than omega c. If omega is negative, then magnitude of omega, or absolute value of omega, is minus omega. So minus omega greater than omega c, or omega less than minus omega c. Okay, so we have this frequency response, which means that all those frequency components with frequencies greater than omega c or less than minus omega c will be passed through the system, and the low frequency components, the frequency components with frequencies in the interval from minus omega c to omega c, will be rejected. Again, omega c is called the cutoff frequency. Cutoff frequency. Okay. Now the third ideal filter we are going to discuss is also important in several applications. The ideal bandpass filter. So the abbreviation is bandpass filter, BPF. Okay, here, as the name implies, frequency components in a certain band of frequencies will be passed by the system and the others will be rejected. So we can define h of omega in this case as follows. H of omega is equal to 1 when magnitude omega, that means absolute value of omega, is between omega 1 and omega 2. Here we choose omega 1 and omega 2 as positive constants, with omega 2 greater than omega 1 and 0 otherwise. Now again, absolute value of omega between omega 1 and omega 2 implies omega is, for positive omega, omega is in between omega 1 and omega 2, and for negative omega, negative values of omega, between minus omega 2 and minus omega 1. So if we plot h of omega as a function of omega for the ideal bandpass filter, let us choose omega 1 and omega 2 like this, and so we have minus omega 1 and minus omega 2. So h of omega is equal to 1 if omega is between omega 1 and omega 2, or between, for the negative frequencies, between minus omega 2 and minus omega 1. So the ideal bandpass filter will only allow frequency components in a certain interval. A band of frequencies will be passed by the system and the others will be rejected. And finally, we have the ideal band stop filter. Ideal band stop filter, which is just the complementary case of the ideal bandpass filter. That means frequency components in a certain band will be rejected and all the other frequency components will be passed. So, okay, first let us write down the expression. H of omega will be equal to, okay, 1 for absolute value of omega less than omega 1, and it will be 1 for omega absolute value omega greater than omega 2 and 0 otherwise. Okay. So if we plot the frequency response as a function of omega, again, for the ideal band stop filter, we are going to have the frequencies omega 1 and omega 2 and minus omega 1 and minus omega 2. So the interval absolute value of omega less than omega 1 means omega is between minus omega 1 and omega 1. So here the frequency response is equal to 1. Then omega, magnitude omega or absolute value of omega greater than omega 2 means for omega greater than omega 2 or less than minus omega 2, again the value will be equal to 1. But all the frequency components in the band for omega between omega 1 and omega 2 or minus omega 2 and minus omega 1, those frequency components will be rejected by the filter. Okay, these 4 types of filters are quite important in several applications. Of course, the most important case is the ideal low-pass filter because it is used in several applications. And of course, the bandpass filter is maybe also quite as important as the ideal low-pass filter. In the ideal low-pass filter, we see that low-frequency components are passed and high-frequency components are rejected. So this acts like a smoothing action on the input function. So if, for example, the input function contains discontinuities, those discontinuities will be smoothed out. That means the output will turn out to be a continuous function because of the fact that high-frequency components are closely related to the sudden jumps or sudden variations in the signal. Okay, thanks for watching.